Hello, welcome to this chapter about propositional logic. Today, we'll understand how different propositions form logic using the principle of connectives. Let's start with the definition. A proposition is a sentence that is either true or false, but not both. For example, the only positive integers that divide 7 are 1 and 7 itself. This sentence is a proposition and it is a true statement. Let's consider some more examples. The set of real numbers is finite. We all know that the set containing real numbers must be an infinite set, which makes this statement false. Despite being false, this sentence is also a proposition because it has a definite meaning and does not imply ambiguity. The next statement is sit down please. We cannot say that this sentence is true or false since it is a command. This means that it is not a proposition. First, let us see some important notations. All propositions would be denoted by lowercase letters like p, q, r, and so on. We will define the statements in such a fashion. P to be the proposition, the only positive integers that divide 7 are 1 and 7 itself, and also Q to be the proposition, the set of real numbers is finite. In ordinary speech and writing, we combine propositions using joining words like and or. We can do the same thing in logic by introducing the so-called connectives. Before we go on to connectives, let us see what truth tables are. Let us consider a compound proposition P, which is made up by individual atomic propositions P1, P2, P3, and so on till Pn. The truth table of P lists all possible combinations of truth values for P1, P2, and so on, and for each such combination lists the truth value of P. Please note that we'll be representing T for true and F for false for denoting values for each proposition. Now on to connectives. We will start by understanding what connectives are. Connectives are mathematical symbols which are needed to combine propositions into compound propositions. Let's start by seeing the first connective, and. And, which is represented by the caret symbol and is used to denote the conjunction of two propositions. Let P and Q be two propositions. The conjunction of P and Q is denoted by P caret symbol Q, which is read P and Q. The value of the conjunction would be true if both the propositions are true. That means truth value of P and Q is true only when both P and Q are true. Otherwise, P and Q is false. The truth table for AND could be drawn in such a manner. Here we see there is only one true value. This is the case where both P and Q are true. In all other cases, AND leads to a false. Let us understand better with an example. Since propositions are mainly representations of logic from English statements, let us consider the following two propositions. Proposition P means today is Monday and proposition Q means today is sunny. As we saw earlier, the conjunction of two propositions would be represented with a caret symbol between them. We can say that the conjunction of the above two statements P and Q would be represented as P caret symbol Q, which means today is Monday and today is sunny, which basically means that today is both Monday as well as is sunny. And is a conjunction. On the other hand, or performs disjunction of two propositions. The disjunction is represented by a reversed caret symbol, which looks like the alphabet V. Let P and Q be two propositions. P, reversed caret symbol Q, which is read as P or Q, is the disjunction of two propositions P and Q. It is defined by saying that the truth values of P or Q is true if any of the propositions are true. P or Q is false if both of them are false. Similarly, this is the truth table representing the OR operation. We can see for each truth value, there is a corresponding truth value in the resultant set. Let us see an example for the same. Considering the following two propositions, P and Q, where P is Team A wins if Paul plays and Q is Team A wins if Quinn plays. The disjunction of the two statements would be represented by a P reversed carry Q, which would be pronounced as P or Q, which means Team A wins if Paul plays or Team A wins if Quinn plays, which basically means Team A would win if either of Paul or Quinn play, or even if both play. Now we will see the not connective, which is represented by the negation symbol. It simply negates the value of the preceding proposition. If originally the value of the proposition is false, after negation it would be true and vice versa. We will use this connective extensively in the next section where we will discuss different theorems. We have a very important connective called the implication. Considering two propositions P and Q, the compound proposition P implies Q is called the conditional proposition and is understood as if P then Q. Here, P is often referred to as the hypothesis and Q as the conclusion. P implies Q is true if both the hypothesis and the conclusion are true. If the conclusion is false but the hypothesis is true, the implication must be false. We can list the truth table over here for the two cases we mentioned. It is not common in correct language, but just in the cases where a hypothesis is false, it does not make the sense for the implication to be false, irrespective of what the conclusion is. We say that P implies Q is vacuously true if P is false, irrespective of the truth value of Q. We can finalize the final truth table as shown. Let us understand how implication works with an example. Consider the following statements. X equals 20 implies x minus 10 equals 10. The English text could be represented as P implies Q, where proposition P is x equals 20 and proposition Q is x minus 10 equals 10. Let's consider another statement. If you score 75% or above in this class, then you will get a distinction. This is a straightforward implication sentence composed of an if-then structure. We can represent the same in the notation of P implies Q, where P is scoring 75% or above and Q means getting a distinction. Let us explore a special case of implication now, the case where hypothesis is false. Considering the two propositions P and Q, where P means 7 is greater than 9 and proposition Q means Barack Obama is the POTUS. We can define P implies Q, which basically means if 7 is greater than 9, then Barack Obama is the POTUS. The defined conditional proposition is said to be true because hypothesis P is false. It does not matter if Q is false or true. We will now examine an important connective, the equivalence, symbolized by the equivalence operator. Considering P and Q to be the propositions, we can say that P equivalence Q is called a biconditional proposition and is read P if and only if Q. The equivalence is true only if both the propositions hold the same truth values. Let us take an example. Considering two propositions, proposition P means the father of Eric is named Derek and proposition Q means the child of Derek is named Eric. We can say that P is equivalent to Q since both statements mean the same. The father's name is Derek and the child's name is Eric. If either of the statement is false, the other must be false. If both have different truth values, the equivalence connective results in a false truth value. Before we finish this lecture, there are some important things to mention. The equality operator, which we see in mathematics, is not a connective. The connective is the equivalence operator. The equality operator is used in place of equal symbol to remind ourselves that we are doing statement calculus, not arithmetic. It basically allows us to compare statements. Moving on to the last topic of converse and contrapositivity, let P and Q to be two propositions. Proposition Q implies P is said to be the converse of the proposition P implies Q. Proposition negation Q implies negation P is the contrapositive or the transposition of the proposition P implies Q. We will discuss more about this in detail in the next section. Thanks for watching this lecture.